This morning we are having the Boltzmann Medal ceremony, and as you all know, the Ken Wilson was the first recipient of the Boltzmann Medal in 1975, and he passed away last June 15. And Joel Leibovitz let us know the sad news immediately to the local organization committee. And then we thought a short session in memory of Ken Wilson would be appropriate. So we are having this special session. Here, the Leo Kadanoff couldn't come, but he sent us some manuscript to be read by Stefano Rupo. So first, let's start with Stefano.
This manuscript was sent by Leo Kadanoff a few days after the death of Ken Wilson, and you can find it also on the web, so we put it on the archive. And I will read just a few parts of the manuscript. Kenneth Wilson made deep and insightful contributions to statistical physics, particle physics, and related fields. He was also a helpful and thoughtful human being. Ken's accomplishments in physics started with contributions to particle physics. And in about 1970, he realized the close connection between approaches that could be used in particle physics and those that could be applied to the statistical mechanics of phase transitions. The focus upon phase transitions produced a set of remarkable important contributions to physics via the synthesis and construction of the modern renormalization group technique. Wilson used the threads of many previous authors, but wove them together with several essential pieces of his own invention. The first of these new contributions was his inclusion of all the different interaction terms consonant with the symmetries of the problem under consideration. In addition, he made innovative use of the fixed point concept to tie together the entire analysis. However, new tools form but a small part of his contributions to renormalization. Prior to Wilson's accomplishments, renormalization, even as applied by such greats as Feynman, Tomonaga, and Schwinger, was a method of dubious validity and only of partial respectability. After its modern construction by Wilson and others, the renormalization group has appeared in thousands of papers devoted to the development of understanding of physical, social, biological, and financial systems. However, renormalization is substantially more than a technical tool. It is primarily a method for connecting the behavior at one scale to the phenomena at a very different scales. It serves, for example, to connect the physics at the scale of an atom with the observed macroscopic properties of materials. One might argue, and I believe that argument, that the connection among the laws of nature at different scales of energy, length, or aggregation is the root subject of physics. One would then argue that Wilson has provided us with the single most relevant tool for understanding physics. This is, of course, Ken's main accomplishment, but is not all. He has helped add to our profession a new style of work and of thinking. When he said that we should do renormalization by looking at all the coupling that might arise with a given symmetry, he was asking for something impossible. Nobody can keep track of hundreds of different couplings, but a computer can do so. Wilson was implicitly suggesting we could gain understanding by asking what a computer can do, and then what we ourselves might do by either using or emulating computers. Ken's engagement in the use of computers naturally developed into an interest in development of methods for supercomputer calculation, which then included a sponsorship of proposals for supercomputers and supercomputing centers, and then morphed into the design of a complex of computer programs which might make possible flexible use of very large computers. The computer work was in part carried out with Kent's wife, Alison Brown, who is a computer scientist. Another subfield engendered by Wilson's work is lattice gauge theories. In this area, one constructs computer simulations of a field theory, often quantum chromodynamics, by doing renormalization calculation in which the field variables are placed upon a lattice. Wilson did the first calculation of this kind, which has now been followed by many others. The result were concrete realization of quantum chromodynamics, which have enabled the calculation of many of the parameters of the theory. Even given this wonderful breadth of accomplishments within physics, the renormalization effort stands out as Kent's most important accomplishment. Before Kent's work, Dirac could say of renormalization theory, "I might have thought that the new ideas were correct if they had not been so ugly." Afterwards, renormalization became simply a tool for connecting different theories. Ken was unfailingly generous and broadly helpful to the rest of us working in his area. One evidence of generosity is the very careful credit given to previous work and workers in Kent's paper. Moreover, I remember with some gratitude the result of a trip to Cornell where I took to help me understand how fermions might be included in a paper. I was writing about quarks and strings. My visit elicited from Ken a tutorial on Grassmann variables, which I then used in my paper. The brilliance of Kenneth Wilson was dazzling, but he never tried to outshine those about him. He was all quite competent.
Add that this manuscript is on the archive now and will be published as in our proceeding in JSTAT. Next, Professor John Cardy will give a short talk on the title of the Legacy of Ken Wilson.
So it's a real privilege for me to be asked to speak at this memorial session. Okay, I would like to start with an apology, though. I'm perhaps not so qualified to do this as perhaps other people who are here. I really didn't know Wilson that well. I certainly met him on a few occasions. I attended lectures by him, but really I was a graduate student and a lowly postdoc at the time that he was really doing his active work. Nevertheless, I think perhaps I represent a generation of physicists who were completely influenced by his work, and without his work, we would not have been able to do what we were able to. Somehow, I can't make this advance. Okay, so actually, I want to show you this, which is a scan of my copy of the Wilson-Kogut physics reports, which was, which, as you see, came out in 1974, and at this point it became my Bible, and I think also the Bible of many other people at that time. A brief CV, I think you've already seen this. I just want to stress that he was actually the son of a famous theoretical chemist at Harvard, and that he was also, when he was an undergraduate, he was an athletics star, and he certainly retained his interest in physical activities, in hiking and all those kind of things up to within a few months of his death, and I'm very pleased to be told that this was the case. So the way I'm going to present this very brief talk is to talk about what we knew before Wilson and what we knew after Wilson. I don't want to say that Wilson himself was responsible for all the changes in our understanding that I'm going to talk about. That would be much too complicated. One certainly does not want to go into the whole history of the development of the renormalization group, for example, on an occasion like this, but I just want to compare and contrast what happened, what we knew before Wilson, what we knew after Wilson, and Wilson played an enormous role in all the things that I'm going to list here. So before Wilson, quantum field theory and statistical physics were essentially separate subjects. I learned quantum field theory as a high-energy physicist. I also did a course in statistical mechanics where I learned about Onsager's solution to the two-dimensional Ising model, and I didn't really appreciate, or I certainly wasn't told, that these are essentially the same thing. And now we understand that there is a well-defined meaning in which the Ising model is a lambda 5/4 field theory, that lattice gauge theories are essentially statistical physics, and now, fortunately, many textbooks and graduate courses teach these as part of an integrated whole. But at the time, his ideas were certainly met with skepticism, and I'm grateful to Edouard Brezin for this quote. Ken was not easy to understand. Not only had he his idiosyncratic ways of dealing with theories as objects that lead to explicit practical calculations rather than as abstract concepts, but he was forcing us to look at the most beautiful theories. Here he's talking about renormalized quantum field theories as merely effective or emergent rather than fundamental. This was met initially with enormous skepticism, and I believe that was actually the case. Though it's quite interesting that you could apply this quote to another Nobel Prize winner, that is Richard Feynman, who also, I believe, thought in this kind of way. And although their personalities were extremely different, I think that there's a lot in common with Wilson's approach to physics and Feynman's. So before Wilson, I think it's fair to say that the renormalization group was a set of half-formed ideas. That's perhaps overstating it, but what Wilson did was to, as Kadanoff said, was to bring these together in one seamless piece of cloth. And what Wilson did, one of the important things that he did, was to realize that it acts in an infinite dimensional space of couplings close to a fixed point. Some of these are relevant, some irrelevant. And despite this infinite dimensional space, it's still an effective computational tool, though in some cases, for example, the epsilon expansion, we have a small parameter, but that's not necessary. And then the applications to critical phenomena, which was a mass of poorly understood data and a few exact results. After Wilson, we had the explanation of universality, also the explicit form of the corrections to scaling, allowing us to sensibly fit experimental data, and the explanation of crossover behavior, finite size scaling, allowing comparison with numerical experiments. Before Wilson, the role of renormalization in field theory itself was actually poorly understood, as was mentioned in the previous talk. And it was later realized that the best way to understand renormalization in field theory is, in fact, through the renormalization group. And bringing in the idea that is completely accepted nowadays that all field theories are, in fact, just effective descriptions at a particular set of energy or length scales. Quite independently, Ken also brought in the short distance or operator product expansion, and this led to the development of conformal field theories, particularly in 2 dimensions. 2 dimensions is a case where we can push through the Wilson program of classifying all universality classes in terms of conformal field theories. And it also led to an understanding of high energy scattering. It was also realized that, that in order to rigorously construct a renormalizable quantum field theory, you need the renormalization group to actually do this. And just to bring these ideas completely up to date, you can now look on the archive and you can find papers showing how the Wilson renormalization group flows are essentially moving radially in an anti-de Sitter space to a holographic projection of the theory on the boundary. Okay, before Wilson, confinement in gauge theories was poorly understood. It was assumed that a gauge theory would confine color, but why it would, we didn't really know. Once you formulate these theories on a lattice, it's completely obvious why they should confine, and also the formulation of lattice gauge theories was, in a sense, ahead of its time because the computational power was not then available, but once it was, they became a major tool in particle physics. One should also mention the invention of the Wilson loop as a new kind of non-local order parameter. Originally, it was meant to actually test for confinement of color, but nowadays you will find as many papers in condensed matter physics applying it to, for example, topological states of matter as you will in high energy physics. Before Wilson, the use of computers to understand fundamental physics rather than more applied physics was somewhat suspect. One was supposed to do analytic work. Okay, that was the only respectable way of actually doing fundamental physics. Nowadays, that's not true, and as Leo said, Wilson taught us to think like a computer, and I love this quote, which I found in an interview with Wilson about his work on the Kondo effect, where he basically solved the Kondo problem using a computer. And it said, looking at the Kondo effect, does this idea come from Anderson, and he says, no, I bought a new HP pocket calculator and I wondered what I could do with it. And I can't take my eyes off it, and I have to figure something that I could do with it, so I run a very simple version of the renormalization group on the Ondo problem. So he was asking the idea, we have these new computational tools, what can we actually do with them? And in fact, Wilson's solution of the Kondo problem using a computational RG method was really, I believe, a major turning point in theoretical physics. It was later adapted successfully by his student, Steve White, as the density matrix RG method, and this led to all kinds of other interesting developments. His ideas weren't always successful. I believe he actually spent a lot of time trying to apply RG ideas to quantum chemistry, trying to solve some of the problems his father was actually worked on. So that didn't really work because somehow the separation of length scales is not necessarily there. But as we've heard, he was an early advocate for the foundation of supercomputer centers. And in fact, he was really a computer visionary. And I'm thankful to Michael Peskin for this quote here. In 1976, he gave us a lecture about how one day we would all be sitting on the beach with personal computers that ran Unix and using them to play games that involved exploration in 3 dimensions. Well, that's, of course, what we've been doing, but this was in 1976, certainly a vision. Before Wilson, early physics education was not a priority for research physicists. We just wanted to actually get on with our research and not bother too much about the preparation of younger people. And he actually used his Nobel laureate status as a way of influencing educators and policy makers, advocating a hands-on practical approach, which he called physics by inquiry. And this led to important reforms at the state and the national level. So, as a summary, Ken Wilson's advocacy of large-scale computing revolutionized our view of theoretical physics, but his understanding of the renormalization group, as Leo said, I think revolutionized our view of the world. Thank you very much.
Next, Gianni Yona La Senior will add some brief personal reminiscences of Ken Wilson.
Well, I'm glad to add a few words to what has been said before. I met Wilson very early. He was in his 20s. He came to Rome for a few weeks, and there was not a great difference of age between me and him. And he was recommended to us by Sergio Fubini, who was a well-known physicist, especially at that time. And he said, look, this is an extremely intelligent person, so discuss with him. Then I found out that it was not easy to discuss with him. He was very reserved. But then that is how our interaction started. Then I met him again. That was happened at the beginning of the 60s. Let's say in 65, I was at MIT, and he came to give a seminar. I like to mention this occasion because I think that his way of doing renormalization group and renormalization theory has really been a turning point in many respects. And so it has been one of the important achievements of the second half of the theoretical physics of the 20th century. So he came and gave a seminar. The subject of the seminar was on the renormalization of fixed meson theory. That was true law theory of nuclear-meson interaction. And actually, that was the way he started developing his ideas. He was not at all interested in critical phenomena, nor was I. We were both particle physicists at the time. For some reason, personal reasons, I could not attend the seminar. So the day after, I asked my colleagues in MIT, so how was the seminar by Ken? And they told me, oh, you see, he's an extremely intelligent person, but what he told us was not so interesting. But that was the main idea of his renormalization group. So it was not at all understood, as often it happens with innovating ideas. And the explosion came after, when there was the great interest on critical phenomena, and came closer of statistical mechanics and quantum field theory became very important. And I think Wilson's ideas influenced a lot of other disciplines. First of all, quantum field theory. In the constructive approach, Wilson's idea was implemented in a very strong way by Gallavotti, another Boltzmann medal. And also it influenced the probability theory and also the theory of dynamical systems. So it has been really a turning point with respect to many problems in the theoretical physics of last century. So I think it's very sad that he passed away it has been one of the most remarkable minds of course, once there was this explosion of interest in the critical phenomena, we met very often. We attended essentially the same meetings, and so I had many occasions to interact with him, and I had started with the field theoretic version of the normalization group, but his way of doing, which is entirely different, it's conceptually different. In the end, they come out to be the same things, but the approach is really different, and it required a remarkable intuition to set up his own approach. Okay, thank you.
Thank you, Zeoni. This will close the Ken Wilson Memorial session, and there will be announcement from local organizing committee.